Um, Welcome. Today our webinar is Climate Extremes in Present and Future. How can we avoid the worst? Featuring guest speakers Dr. Philip Mote and Dr. Sonia Seneviratne. My name is Leslie Marasco. I'm the Student Diversity Program Manager here at AGU, and I'll be your host today. First off, just a couple logistics items. We'll have a Q&A at the end of the presentation today, so if you think of any questions throughout, just type them into the question box, the same place where you just let us know where you're coming in from, and we'll answer as many as we can at the end of the presentation. Additionally, we'll ask you to reply to a couple poll questions today, so keep an eye out for those during the presentation. And finally, we'll send a link out to the recording at the end. So in the next few days, just keep an eye on your inbox. Next, I'll introduce Dr. Philip Mote, who will be introducing our guest speaker today. Dr. Mote is the president for AGU's Global Environmental Change section. He is the vice provost, dean of the graduate school, and professor in the College of Earth, Ocean, and Atmospheric Sciences at Oregon State University. And with that, Dr. Mote, I'll pass the mic over to you.
Thank you, Leslie, for your help setting this up. And on behalf of the Global Environmental Change section, I want to welcome all the attendees today. It's a great privilege to host Sonia Seneviratne as our second centennial webinar speaker. This is an experiment that GEC decided to do, led by our early career folks who are interested in connecting electronically. Dr. Seneviratne is a professor in land climate dynamics at ETH Zürich. She studies various aspects of land climate processes, climate extremes, using modeling and observations. In 2013, she was awarded the prestigious McElwain Medal of the AGU and was also elected fellow that year. So I will turn it over to Sonia now.
Yeah, thank you very much, Phil. It's a great honor to give this presentation, also a great pleasure. So yeah, thanks for the invitation to you and also to AGU. So what I will talk about today is about climate extremes in present and future. And yeah, Phil asked me to give a very general presentation. So my question is, how can we avoid the worst? And they are mostly focused on work and conclusions from the IPCC special report on 1.5 degree warming, as well as some work that we have within our research group. I want to point to two pictures I've included on my title slide. The first picture is from my research group. I just want to thank all of them for their contributions. I will present several of their results, especially from Marta Vogel. And the other picture is from the authors of the IPCC special report on 1.5 degree warming. It was a great team to work with. I was also one of the authors, and so obviously this is a joint work from all of us. So actually, I will start with the first poll to the attendees. I was interested to know for you what would be the worst and what should be avoided. The first question was first possible options are lower quality of life in many countries, higher inequality, many deaths due to climate disasters, irreversible loss of biodiversity and of humankind, or all of the above.
So if you could make your selection, we'll give you a couple more seconds to kind of read through the options and make your pick. All right, we have almost 50% of all attendees voting, and we'll close it out in 3, 2, and 1. Okay. So it looks like, can you see the results, Sonia?
Yeah, I can see the results. Yeah, thanks, Leslie. Yeah, so yeah, most people choose all of the above, and yeah, I think that's, I guess the main message I wanted to bring up with this is that, of course, there are different ways in which we can define, what is worst. In the end, probably we want to avoid all of those different aspects. Some discussion is always talking of just a collapse of humankind, but probably we should have a different benchmark. We should also avoid many other impacts of climate change. So I come to, to where we are now. That's one of the first conclusions from the IPCC special report. We already have 1 degree of global warming. And I think for me, a really important point is this warming is irreversible on the time scale of present generations. So the CO2 we are emitting through the use of fossil fuels is staying in the air for several hundreds to several thousand years. This means that whenever we reach a given level of global warming, we cannot go back. Basically, this level of warming is something we have to live with. And that's a really important point. Now, again, in terms of where we are at the moment, I think it's important to see that climate change is not something happening in the future. It's something that is already happening now at present. And so there are detectable changes in climate which can be attributed to human CO2 emissions. And of course, it's mostly due to consumption of fossil fuels. In terms of climate extremes, and that's one of the conclusions of the IPCC special report, but also based on previous IPCC report, we can already detect and attribute increases in heat waves and hot extremes in most land regions, also increase in heavy precipitation at global scale, increase in drought in the Mediterranean region, as well as more intense precipitation associated with tropical cyclones. So we know already climate extremes are increasing at the moment. They're already having impacts on our world as we know it. So when does it get too much? I mean, that's actually the main question. When do we want to stop? And for this, I think it's a difficult question. To some extent, this question is not entirely a scientific question. It's also a question of choice, societal choice. I tried to think of some analogy we could think of to illustrate this problem. I was thinking maybe one good analogy would be considering that we are on a kind of platform and the human CO2 emission are pushing us always further up. And there is a lot of wind, people can fall from time to time. And at the moment, so we have 1 degree, we are about 1 meter above ground. Now, of course, some people might fall down. It's somewhat dangerous. It's not too bad. Maybe you can twist your ankle. So when does it get really bad? Now, let's say that we would continue to emit CO2 and we continue to basically have a higher platform. At 1.5 meters, maybe we might have a broken leg if we fall badly, or at 2 meters, it gets already much worse. You could have multiple injuries and maybe some irreversible injuries. Now, of course, the vulnerability is different for different people. Some people might be able to fall better, and also, of course, if you are considering a small kid or a baby, this baby could already die if it were to fall from 1.5 meters, for instance. Now, if you add further increase, so further elevation of this platform, at about 3 meters, of course, we would have irreversible injuries that maybe you might become paraplegic. And possibly at 4 meters, you could die. So the question of what is the worst and what do we want to avoid? Probably we want to avoid most of those negative impacts. And it means that already now we are in a situation where we want to avoid having more impacts than we are already having at the present. But I just wanted to illustrate this question of gradual impacts and the fact that probably we want to avoid, in any case, the worst impacts that we could experience. Maybe one point to mention is you could even have some tipping points. Maybe at some point the platform could become unstable. And so that's an additional point we need to consider, although probably science would not be very robust on this point. So you could have, of course, some counter arguments. Some people could say, oh, we can put a barrier, a mattress, maybe the kids can be harnessed, or maybe we need to develop further to have adequate protection against this danger. And some people might say, oh, but I don't think 4 meters is that risky. I'm sure I'll be fine. Sorry. But so the science is just telling us that we are increasingly putting ourselves and our environment at risk. So basically, we need to stop. And in terms of CO2 emissions, in terms of impact on climate change, this means reaching net zero CO2, and the earlier the better. So the earlier we manage to do this, the less impact that we are going to have. I was trying to think of another analogy, maybe in terms of health, just also to illustrate that in other contexts, also very small changes in temperature can have major impacts. This is a chart about how to react to fever when different people have fevers. And so in small kids, already a fever of about 0.5 degree or 1 degree would be a reason for concern. So, I mean, when we are saying that climate change is a difficult or complex issue, Actually, we have examples of such complex issues in our everyday life. We know that differences of few degrees can matter for our health. We can take complex decisions under uncertainty, so we can decide if our kids are sick, whether we have to go to the doctor or not. We do understand the concept of different vulnerabilities. We know somebody would be older, would have less problems than a younger person. And we care also about others' well-being. We are going to take care of our kids, our relatives, our friends, or our patients. So to some extent, a lot of the issues we have with climate change is not something that we are totally unfamiliar with, and we should be able to address this issue. So to this extent, can we extrapolate this to climate change? Are we able to address this challenge? So the main point I want to highlight in my presentation are the following. First, I want to discuss how regional climate extremes change at different levels of global warming. Then I will discuss briefly some work which is more related to our research about the importance of land forcings and feedbacks for regional responses. And finally, I will discuss pathways to 1.5 degree warming. So for the first question, which is how do we relate given the warming levels, global warming levels to change in regional extremes, I will mostly base this on the IPCC special report on 1.5 degree warming, which was approved in last October. I have a picture here of the approval session, and I was very privileged to be able to attend also this approval session. So the context for the 1.5 degree warming report from IPCC was the Paris Agreement for 2015. And so the aim of the Paris Agreement, which has been signed by all UNFCCC members, is to limit global warming well below 2 degrees above pre-industrial levels, and to pursue efforts to limit the temperature increase to 1.5 above pre-industrial levels. And so I think this is really something we have to repeat. I mean, this has been signed. All UNFCCC members have committed to this goal, even countries which officially seem to have more critical stances against climate mitigation, for instance, the US, Saudi Arabia, or Russia. So in terms of the link between global warming and the CO2 emissions, there is very clear evidence from the last IPCC report, the larger IPCC report that was published in 2013. This is a really important figure, which is showing how change in global mean temperature are related to cumulative CO2 emissions. So as mentioned, the CO2 accumulates in the air, and it stays there for several hundreds to 1,000 years. Now, for a given total amount of CO2 emission, we have a corresponding global warming. This means that if we set a global warming target, and that was the point of the Paris Agreement, this automatically sets also a given CO2 budget, which we shouldn't exceed if we don't want to go beyond this global warming level. Now, as mentioned before, we already have 1 degree of global warming. This means that we have an extremely limited CO2 budget if we don't want to go beyond 1.5 degree warming. And even for 2 degrees, this budget will be very limited. As we see here, if we do nothing, if we don't act, we would reach 1.5 degree warming in about 2030, so in a bit more than 10 years. So this means it's really urgent. Not acting is also a decision that has consequences. Basically, having inertia, having no decision, having no action doesn't imply that there wouldn't be any change. In the contrary, it's also a choice, and it's a bad one, because we will continue to have further warming and more impacts. So now I want to come to the question of how can we relate those changes in global warming to regional changes in climate extremes. And actually I have a second poll here. And my question here is, by how much are cold nights projected to warm on average in the Arctic, when on average you have 1.5 degree global warming?
All right, we got some votes coming in. So make your selection for how much you think the average temperature in the Arctic would change at 1.5 increased global warming. Gonna wait just a few more seconds so everyone can get a chance to vote. All right, we're gonna close it out.
Okay, so it's an interesting result. So most Persons answered 3 degrees, and actually the correct answer is 4.5. So on average, for the coldest night, the model projections show a 4.5 degree warming of at 1.5 degree of mean global warming. So you have basically a 3 times larger warming in the Arctic than on average. And that's one of the important points. In many locations, we have much more warming than in the global average. This is what I'm going to show in the next figure. So this is showing the projected changes in the local climate extremes. On the left, in the temperature of the hottest days, and on the right, the temperature of the coldest nights, when on average you have 1.5 global warming, but you see that regionally, locally, you have much warming. So the hottest days, you have up to 2 to 3 degree warming in many locations. For instance, in Central Europe, the Mediterranean, many parts of the contiguous United States. And for the cold nights in the Arctic, we have very large warming, so more than 4 degrees and average about 4.5 degree warming. So as you can see, basically having 1.5 degree of global warming does not imply a 1.5 degree warming everywhere and all the time. And the important point there is that we have much more warming generally on land, inland regions where we are living. So that's something that's often underestimated. Now, just to illustrate this relationship, this is an analysis showing how temperature extremes, so the hottest days, are changing in the Mediterranean region. This is based on climate model simulations, the global simulations that are available from the CEMET 5 archive. This is showing how the hottest days are changing as function of global warming. The red shading is showing all of the simulations, and the red line is showing the mean of this, so the multimodal mean of the RCP 8.5 projection. In blue, you have the multimodal mean for the RCP 4.5 projections. And interestingly, we find that the relationship is almost linear. So we can very well infer what is the regional response at different levels of global warming. There is some spread between models, but in this case, it's relatively limited. And what we see, as mentioned before, is that we have more warming there in this region than for what we have in terms of global warming. So the dashed line here, the 1-1 line, would be the global mean temperature change. You see that at 1.5, we are clearly above this. So we have about 2.5 or up to almost 3 degrees of warming, depending on the model. So we have a robust and almost linear scaling, which is mostly independent of the emission scenario. So you see that the dependency is not really dependent on the emission scenario. It's about the same for the lower emission scenario and the higher emission scenario. This means that there is a clear relationship between how much global warming we have in the scenarios and what is the response on regional scale. We find this type of scaling also for other variables, for instance, for the warming of the minimum temperatures and change in heavy precipitation. On the left here, I'm showing the projected changes in the coldest nights. That's what I was referring to in the poll. So for instance, here at 2 degrees, we have 6 degree warming, so 3 times higher warming. And so at 1.5, it's about 4.5 degree warming. That's again for the multimodal mean. For some models, you have higher levels of warming. And so even at 1.5 degree warming, for instance, you could have 6 degrees according to some models. For heavy precipitation, we find also a quite clear relationship between the multimodal mean response, but we have much more spread. But clearly, for instance, at 2 degree warming, we could have very large increase in heavy precipitation, but according to some other models, maybe a bit weaker one. In any case, there's a tendency towards increase in heavy precipitation here in Southern Asia. So global warming levels can be linked to regional changes in extremes, and in some cases we can have very large changes even at low levels of warming, as we have seen for the Arctic. And that's really important because sometimes subjectively you might think that 1.5 degree warming is not a lot, especially when we're thinking of this in Celsius, but it actually implies very large increase regionally in several locations. Now the next question is, does 1.5 degree climate substantially differ from climate at 2 degrees, and you see substantial differences in climate extremes. This is an analysis that is based on a study from Richard Wartenburger, which we also considered in the IPCC report. And it's showing for all of those different regions, which are shown here at the top, so these are IPCC regions, to which extent we find a substantial difference in those extremes between 1.5 and 2 degrees of global warming. The two first indices are temperature extreme indices. The T6 is the hottest day of the year, the ENN is the coldest night. And you see that for all of these indices, we find substantial differences between 1.5 and 2 degree warming in actually all of the regions. For heavy precipitation, we find that there are many locations where there are substantial differences. So there is RX5D is a heavy precipitation index, and there are increases in many locations, as you can see here in this line. Finally, CDD is consecutive dry days. It's a measure of dryness. Here, the response is a bit less clear, but positive signs, so an increase would suggest more tendency towards dryness. And in several regions, actually, we find a significant difference, a significant increase in CDD. So towards dryness, for instance, in the Mediterranean here, also in Central Europe and in Southern Africa, just as some examples. So yes, there are substantial differences between occurrence and the intensity of extremes at 1.5 degree warming versus 2 degree. To summarize the main conclusions of the IPCC special report, what we found is that, based on the available literature, is that the limitation of global warming to 1.5 compared to 2 degrees allows to avoid substantial additional change in extremes and impacts. The increases in hot extremes in most inhabited regions of the world, heavier precipitation in several regions, also increased drying in some regions, in particular in the Mediterranean and Southern Africa. And what is also very important, some irreversible impacts, for instance, increases of sea level rise, extinction of some animal and plant species, and in particular coral reefs. So that's an additional important dimension, which is above 1.5, there is evidence that we are starting to reach into irreversible impact, so we can not go back. This is one main summary of the report, which is looking at the sensitivity of different systems to global warming levels. So it's showing different levels of risk, and white would indicate undetectable risk. Yellow is moderate risk, red is high risk, and purple is very high risk. 1 degree, as mentioned, is the present level of warming. So what you see is at present, with the present level of warming, we are already having very high risk for warm water corals, and we would switch to very high risk at 1.5. So in some cases, already the present level of warming is associated with high risk and would get to very high at 1.5. Other very sensitive systems include, for instance, the Arctic, where we have a switch from high risk to very high risk between 1.5 and 2 degrees, and also coastal flooding, also a shift between high risk and very high risk. So we see that, of course, for all of those different systems, the critical thresholds are different, but we have, of course, an increase in risk for all of them with higher levels of warming. So we have some irreversible impacts above 1.5 degrees of warming. And so one of the conclusions of the report was that every half of degree matters, in particular given those conclusions. Now, of course, a topic that is of high interest is the question of a tipping point. This was also assessed in the report. I think we should consider both the regional tipping points for systems, so unique as threatened system, which is showing that we have some local tipping points between 1.5 and 2 degrees. Regarding really large-scale singular events, which is often what is meant by tipping point, we have a switch between a moderate to high risk, between more or less 1.5 and 2 degrees. Here, the uncertainty is only medium because obviously these are systems that are not very well understood. But actually, in this case, uncertainty should rather push us to take a precautionary position. This is an illustration of analysis of tipping point, which is showing that, for instance, in the literature, many tipping points are detected between 1 to 2 degrees of global warming, but obviously with high uncertainty. Another important question is the question of compound events. So the fact that you could have several events of different types happening in the same location, or several regions being affected by extremes at the same time. This is an important new topic that was not addressed in detail in the 1.5 degree report, but that will be addressed in more detail in the new report from IPCC that will come out in 2 years. Just to show an example, the 2018 summer was very extreme in a large part of the northern hemisphere. So there were fires, hot extremes, droughts in many locations. And in terms of the hot extremes, a study from Martha Vogel has shown, which is currently conditionally accepted in the future, has shown that about 22% of the inhabited area of the northern inhabited area, but also area where there is crops being grown, was affected by hot extremes. And this was unprecedented. On the other hand, given the fact that we have now 1 degree of warming, we could expect this type of extreme events at a chance of about 10%. And at higher level of warming, for instance, at 1.5, it would happen about every 2 out of 3 years, and at 2 degrees, almost every 2 years. So we see also this co-occurrence of extremes would be an increasing risk with increasing warming. Last point I want to mention is underestimated feedbacks. Obviously, climate models are not perfect, but that doesn't mean that we shouldn't shouldn't consider this with caution. To some extent, actually, it should push us to be even more conservative in terms of our response or in our addressing climate change. So they may also underestimate responses of climate change. Just one example here is a study from Vincent, which is showing that we have a relationship between the increase in CO2 in the atmosphere and the variations in water on land. We find a very strong relationship, which suggests that when we have droughts, we have a further increase of CO2 in the atmosphere. This could be explained by less uptake of CO2 by vegetation. What we found in that study is this relationship is underestimated in current climate models. So this is a potentially important feedback that may be overlooked and could have strong impacts in the future. So I come to the second point, and I will hurry up a little bit. It's about the importance of land forcings and feedbacks for regional responses. And I wanted to come back to the scaling plots I was showing before and showing how land processes play a role for those projections. I'm focusing here on 2 regions, the contiguous United States and Central Europe. And in those regions, we find that the projected changes in hot extremes here show a very large spread. So the multimodal mean is still more or less linearly related to global warming, but we have a very large spread. So for instance, at 2 degrees, we have anything between almost no warming and up to 4 degree warming in the contiguous US. In Central Europe, anything between about 1 degree to 6 degree warming. So we see that we have substantial spread and uncertainty. Those regions are regions where we know we have strong soil moisture feedbacks. This has been shown in several studies, for instance, some from our group. And basically, making it short, the idea of soil moisture feedbacks is those regions that are sensitive to them. And basically, you have switched between a wet and dry soil moisture regime. When you have wet regimes, you have more latent heat flux, and when you have dry regimes, you have much less latent heat flux, more sensible heat flux, and this leads to an additional warming. And so in those regions, it means that whenever you have a switch to drier condition in a given summer, you could have much higher temperatures. Now, in a study from Martha Vogel, which was based on the Crisis 5 experiment from a few years ago, we found that much of those hotspots we found in the hot extremes, this is a map on the left, is showing in the highest emission scenario, the change in temperature extremes. And you see again those hotspots where we have very large increase in temperature, while those hotspots disappear if we prescribe soil moisture to the conditions of the late 20th century. So we don't allow for drying in the land model, and we see how the atmosphere is reacting. We see much of those hotspots disappear. Now, if we look again at the scaling, what we find is that without the soil moisture feedback, we are back on the 1-1 line, which means that this is the blue shading here. This means that without soil moisture feedback, we would have more or less the same warming also in those regions as on the mean global average. And so this amplification that we found was mostly due to soil moisture feedback. So just to summarize this very quickly, to some extent, this is showing that the regional response here, which is actually the red simulation, is the addition of the global climate sensitivity. So our global temperature is depending on CO2, and then this additional regional amplification, which in our case is mostly related to soil moisture feedback. So you can use observation to constrain projections. We have found that there was this very large spread. So obviously, it would be interesting to use observation to try and reduce uncertainty. And for Central Europe, a study from Marta Vogel is showing that if we use observation, we can reduce the total spread. And we can distinguish between dry, very dry, and wet models. And actually, the more realistic model is this distribution here, which is a bit less extreme than the original distribution. So obviously, knowing which processes constrain those projections help us to also reduce uncertainty in projections. So now we have seen that land processes play a very important role. This was looking at land feedbacks, but also land forcings can be essential, for instance, land use and land cover changes. And this can include both different agricultural practice, for instance, irrigation, also changing land cover, so for instance, deforestation or afforestation. So in addition to those land feedbacks, the land forcing are highly relevant for the regional response, and I'll discuss this in a bit more detail afterwards. So I will finish with pathways to 1.5 degree warming. Going back to the 1.5 degree global warming report from IPCC. And so what are the pathways that we could follow to limit warming to 1.5? The pathways that allow us to reach 1.5 degree warming, so to limit warming to 1.5 with no limited overshoot are shown here in blue. And maybe the main message here is that emissions so far do not commit us to a world with more than 1.5 degree warming. So we are not condemned. We are not condemned to have such a world. But it does require change which are unprecedented in terms of scale. So this is the level of emissions at present. And obviously, if we want to reach this type of decrease of emission, we need radical change in our society, in the way in which it is working. So we would need immediate reduction of CO2 emissions. And until 2030, this would be about 50% of what we had in 2010. And we need to reach net zero CO2 emissions at the latest in 2040 to 2015, as we can see here. So these are the two main goals that we need to reach if we want to limit global warming to 1.5. We also need to have some CO2 uptake from the atmosphere, which is called negative emissions, because as you can see, the pathways here go to negative values of emissions. It means CO2 is taken up. This can be possibly reached through reforestation or afforestation, also technologies for carbon capture and storage. But there are significant issues there, and trade-offs should be minimized. Obviously, earlier action helps because then we need to rely less on such negative technologies. Just to say how this can be achieved, a lot of the proposed ways in which some of the negative emission could be reached is through actually changing land use. So for instance, afforestation, also use of bioenergy coupled with carbon capture and storage. As this is shown here in the figures, these are two types of scenarios which are compatible with 1.5 degree warming. One is a very strong increase in forest, another one is a strong increase in energy crops. So I won't go into the details. There are different ways in how this can be reached. There are substantial uncertainties. But the main point here is that those IPCC scenarios that allow limitation to 1.5 include major change in land use because of increased bioenergy use, or also increased bioenergy use together with carbon capture and storage, afforestation and reforestation. There are numerous issues that I won't have the time to discuss, but maybe this will come in the questions. Among other, and as that's one point I really want to highlight, the biophysical feedbacks are generally not considered. So those technologies are only considered in terms of their effects on the carbon cycle, but not in terms of how they affect regional climate. And this could be substantial, for instance, up to about 1 degree regionally. So there are substantial co-benefits. For instance, in case of no-till farming, so you have more residues on the soil, you have increased albedo, so more reflection of radiation, which will lead to additional cooling. But you could have also some trade-off. In case of afforestation, where you have snow cover, regionally, afforestation can lead to warming. So I will finish with a 1.5 degree storylines. This is work we have done within the chapter 3. We have a cross-chapter box illustrating some stories of how we could reach 1.5, or also what would happen if we were not able to reach 1.5. I cannot, of course, discuss all of the details, but I just want to point to a few key aspects of this scenario. So this is in the best case scenario where we manage to limit global warming to 1.5. In terms of mitigation, the main aspects are that we have international coordination. We have an electrification of energy use in the 2020s. We have decarbonization of transport, so more electric cars sold in 2025 than cars with combustion engines. There is also more development of technology for carbon capture and storage, minimization of food waste, and an important point related to the issue with land use that I just mentioned is that the competition between bioenergy production, agriculture, and biodiversity needs are minimized. Finally, there are also decrease in demand, for instance, the social preference for healthy diets with less meat. So I come to the conclusions and outlook. We are at a crossroad at the moment. Major and immediate action can still limit global warming and global heating of the Earth and to 1.5 degree warming, as well as associated changes in climate extremes. And lack of action has direct consequences. So not doing anything is not letting us at the same point, it also has a major impact. So every additional year counts. Land processes play an important role. They need also, in particular, to be considered in association with considered changes in land use. In terms of the long-term solution, whatever global warming levels we want to limit ourselves to, we need to have a net zero CO2 budget, and we need to have no consumptions of fossil fuels, petrol, coal, and gas. And I want to finish with this main message from the 1.5 degree report, which is that every action matters, every bit of warming matters, every year matters, and every choice matters. Thank you.
Thank you so much for that presentation. If you have any questions, be sure to type them into the chat box. We have quite a few that have already come in, so I'm just going to start us off. But if any of you who've been attending that haven't typed your questions in yet, be sure to do that now. So one of the questions that came in is, can new technologies have a beneficial contribution to mitigating these extremes? And you mentioned some technologies, but what are some other ones, and how can these be used to mitigate some of these extreme climate outcomes?
Yeah, so certainly new technologies, I think the easiest answer is just renewable energy. I mean, the renewable energy is becoming much cheaper. So for instance, solar energy is very cheap at the moment. So this means these are certainly new technologies that are available and would be worthwhile to use because first they are cheaper, and in addition, of course, they don't lead to any CO2 emissions. So that's one important aspect. I think that's the main one. Now, on the other side, I also mentioned, for instance, electrification of mobility. It's a bit debated. Of course, there is not the footprint of building an electric car is non-zero. There are impacts for the environment. But still, if you have to choose between an electric car or a car with combustion engines, then the electric car is better for the environment and the climate, considering the use of the car. So, and finally, there is the question of carbon capture and storage. I think we need to be very careful with those technologies. This is not a panacea. It's not going to provide a perfect solution, but we probably need some level of CO2 uptake. So maybe maybe between 5 or 10% of the emissions we have now, maybe, hopefully even less. But we need to have some technologies in this area, but it's not well developed at the moment, so we cannot bet on this at the moment.
Great. This is a little related. Do you think that the rise of sustainable and environmentally friendly practices over the years have helped slow down climate extremes? I mean, we see it accelerating, but do you think that it would have been accelerating at a faster rate had some of these practices not been becoming more popular recently?
Yeah, no, definitely. So there have been reports showing that there have been decrease in emissions in many developed countries. The problem is that the decrease are still too limited. So I mean, I live in Switzerland. I think here it has been about 10%. So there has been a decrease. It's not that all countries have increasing emissions, but the problem is it has been just too little, and we need to reach net zero emissions. So yes, there have been some progress, and it does help reduce some of the impact of climate change, but it's not sufficient yet.
So a couple other questions. How will the warming impact the Bermuda High?
So I cannot answer to that question. Yeah.
Okay. Let's see. How do short duration extreme convention precipitation events could be predicted more confidently under different climate change scenarios?
So how can we reach better prediction of short duration extreme? Yeah. So obviously, I mean, the models are doing an okay job, but they are not perfect. And it seems, for instance, that higher resolution could help simulate some of those extremes. In some cases, also feedbacks I was mentioning with the land surface can be relevant. So there are uncertainties, but it's not to the extent that we cannot have confidence in the projections, to the extent that we basically have confidently an increase in heavy precipitation associated with global warming, if you look at this in global scale.
So we have a couple questions about policy. One of them is how much importance should be given to governmental policies and the reduction in populated areas as a way to reduce CO2 emissions.
So you mean a reduction of population?
And policies around that. So how important should governmental policies be, especially with how the variance between different countries or even states in some countries?
I didn't fully understand. So is the question about what type of policies we should have, or is it related to population?
My understanding is about the policies. How important is it to enact these policies?
Yeah. Well, it's essential to enact policies. There is an intense discussion on this. So as I mentioned, I mean, all the signatory countries and basically all members of UNFCCC have signed the Paris Agreement, and now the latest IPCC report has shown that there is substantial difference between 1.5 and 2. So if they are serious about what they've signed, this means limiting global warming well below 2 degrees and if possible to 1.5. So it will be essential that policies are implemented in all different countries. So each country has their own responsibility to implement the needed policy. There was recently a report from the Climate Change Committee in the UK, and they have proposed some internal goals for the UK where they could reach net zero CO2 emissions by 2050. So some countries are already concretely considering possible options.
And just a follow-up question, as some countries are adopting these, strict policies that may have a financial impact on their economy, how do you kind of navigate the differences between countries when others are blatantly, not on board for reduction?
Yeah, I mean, that's a difficult issue. in the end, I think that's on my last slide, any bit of action matters. So anything that we can manage to do, any reduction of emission will be helping. And some of the help can be also in the form of showing that it is possible. So that's some of the argument we can have in countries like Switzerland, again, where I'm in. But also in the US, I think at the level of cities or single states, there are major efforts that are being done. And you can basically make the case by showing maybe to other countries, other locations, that it's possible to reach this without having necessarily negative impacts. Finally, I do think that countries or regions that start implementing mitigation options first may have an advantage because they are more familiar with those technologies, and they can also then help other countries develop them and implement them.
Great. Another question is if the 2 to 3 degrees Celsius situation is stable, or is there risk for amplified warming, even if the entire population adopts net zero practices?
So I think the further we go away from the reference climate we have experienced, the more uncertainties there are. I did mention tipping points, so we cannot exclude the presence of tipping points, but obviously it's a topic that is associated with large uncertainty. So I would say if we want to minimize the risk, then we need to have the least warming possible, and that would mean really 1.5 rather than 2 degrees or more, because those risks become higher above 1.5.
So you mentioned this a little bit when we were going back and forth about the question regarding policy, but what about urbanization and folks moving, to more highly dense populated areas, and is that an effective tool to be used in climate change?
Yeah, actually, this can be positive. I think so. To some extent, emissions can be minimized in cities because you can use more public transportation. So I live in Zurich, which is a middle-sized city, and here it's really very easy to live without a car. That's not. I don't have a car. I don't really need one. So we have excellent public transportation within the city and also connected to other cities. And so to some extent, maybe living in a city is easier if you want to minimize emissions. So there is certainly potential there. Yeah.
And there's a question about methane emissions and those effects, which is stated that those are sometimes ignored.
Okay. No, they are not ignored, and they are very important. It's an important contribution, especially from agriculture. The one, and obviously that's also one of the conclusions of the 1.5 report, is that reduction of methane emission would strongly help also limiting global warming to 1.5. Now the difference between methane emission and CO2 emission is that methane is much more short-lived. So, but on the other hand, it's a very powerful greenhouse gas. So there would be some advantage in reducing methane quickly, so it would have more impact directly on temperature, but in terms of long-term effect, CO2 is more important. So that's why there's been a bit more focus on CO2 because it has such long-lived effects, but obviously methane is also very important.
And another question about some of the temperature anomalies and how those change depending on the time period and the range that you're looking at. So say, you're looking from the 1880s to 1900 versus, the 1860s to 1920 in like a longer range. And do you see substantial differences when you're, comparing those to different time ranges?
So if we are looking at different time periods? Okay. Yes, so there's been especially strong warming since about 1950, but it's also the time period over which we have had the most global warming. We have analysis which are showing that prior to 1950, for instance, land use was also playing an important role for the change in hot extremes. So there was some warming that was associated with land use, so basically deforestation. So the role of different drivers, respectively land use versus basically fossil fuel consumption, has changed over time. But yeah, the highest increase is since 1950.
And could you maybe expand a little bit on the potential of geoengineering used to help with mitigation?
Yeah, so one issue is that geoengineering is often used as a term both to consider carbon dioxide removal, which would be understood under carbon capture and storage, and solar geoengineering. So basically, the possible emission of sulfate aerosols in stratosphere. So I did mention carbon capture and storage. I think to the extent that CO2 is so long-lived and stays so long in the atmosphere, if we have some technology that would allow us to take up CO2 and store it, it would be part of the solution, but it cannot be the only solution. And at the moment, it's not fully ripe. So at the moment, we cannot bet on this, but it's worth certainly having more research on this. But it doesn't forgoes the need for mitigation. We need really to have major mitigation, so major reduction in emissions. Now, regarding a possible solar geoengineering, which is also sometimes discussed in the literature, we didn't have a lot of assessment on this in the 1.5 report from IPCC. This is, in my opinion, something that is very risky, because it's not really helping. To some extent, it would only mask some of the warming, and so it doesn't have the same footprint as the warming that is associated with CO2. And we also know that if we were suddenly to stop, so the sulfate aerosols that are short-lived, you will need to have injections again every year. It means that you basically commit yourself to a solution that is a solution that is not really one, and is only hiding some of the effects and not all of them. Finally, if this were discontinued, you would have you could have a major increase of warming in a very short amount of time, and there are studies that have shown that this could really have major impacts on ecosystems. So I think the solar geoengineering is very dangerous. It's not a solution.
And there's been another question about if there is a concrete figure on the anthropogenic factors that contribute to global warming, and this, could potentially be really helpful for folks if they are participating in the legislative process within their countries or their states, if they can provide this to, political figures. Do you know of a figure like that that exists that kind of sums everything up that can be provided to other people?
So, I mean, I do know that, for instance, there is a global carbon project which provides the assessment of the carbon cycle every year. And there are clear numbers on, but these are global numbers regarding total emissions. And so more than 80% of total emissions are from fossil fuel consumption, as the rest is deforestation. I assume possibly that there are numbers by country. So the place to look for this would be from the Global Carbon Project. So I could provide a link later on. And it's possible that the IPCC report also includes this in the chapter dedicated to scenarios, and I could check this.
Great. So just for all attendees that are online, we will be sending out the recording of this as well as slides. So Sonia, if you want to actually include that before we post the slides, maybe folks will have access to that. That'd be great. Thank you. So here's a pretty heavy question. So do you feel that Western practices are inherently detrimental to the world, or is there any way to maintain kind of this quality of life that we have adopted in the West of, you kind of mentioned, public transportation, but a lot of people in more rural areas, drive a lot and have just a much bigger carbon footprint, or even like flying to conferences. Flying seems to be much more regular. So do you think that our lifestyle is inherently detrimental?
Yeah, I think there is a lot of debate in the public discourse about, how much of the problem is inherent to basically growth and development, and how much could be solved with technological solutions. I think the truth is probably a bit in between. So we do have technological solutions which are available right there and are not very expensive, and they wouldn't really change our lifestyle, and they could already reduce a lot of the emissions. So again, if we think of people living in rural areas, switching to an electric car would help a lot, and so that would be a first solution. For airplanes, it's very difficult, but first, obviously, probably some of the lifetime might need to be a result that we need to fly less, and if possible, not at all. If I look at Europe, we used to have very good train connections, and if we had this again, but maybe better night trains, for instance, you would not need to fly that much. So certainly there could be some alternative, and it's also not excluded that we could use biofuels to power planes, or possibly solar energy. So I think at least for the first goal, which is reaching basically halving emissions until 2030, so reaching only half of the emissions until 2030, I think a lot of this can be reached with technological changes. Whether we can reach net zero only with technological changes, maybe this is more of an open question. And we'll find out, I think, once we try. So we see how much we can reach with technological solution, and we have to find out if they are sustainable or not. My guess is that it will certainly help also to have some change in lifestyle. So for instance, in terms of food consumption, it was shown that the switch to healthy diets, so it doesn't mean that you wouldn't eat any meat, but just that you would eat maybe meat only once a week. This could help a lot. So there are also certainly lifestyle changes that can contribute.
And I think we have time to squeeze in one more question. So in some of these high-risk areas, especially coastal areas that keep getting hit with these climate extreme events, it seems like a lot of it is just responsive rather than preventative, and it's a huge financial investment. So what would your recommendations be to those at-risk communities?
Yes, so certainly you can help adaptation by being more proactive. But I can't help thinking when you see how much money already needs to be spent to address the impacts of climate change. Certainly we need to invest in mitigation. I mean, that's the best pathway to adaptation is to reduce overall climate footprint, so reducing the overall climate change. And so I would recommend to countries, and I think that's all countries. People died last summer also in Canada, in Japan, in the US, so even developed countries are affected by climate change. You need to be proactive, consider the changes that are already happening now. But on the other hand, the best way really to react is also to have very intense action in terms of mitigation and now reducing emissions.
Great. Well, I think that's all we have time for. So thank you so much for presenting today, Sonia. It's been really eye-opening, and you've provided us with a lot of great information. So thank you for taking the time to share all of this with us. And thank you to all of our audience members who joined today. So keep an eye out for your email. There will be a link to the recording that will be sent out. And also, we have another webinar from AGU that is tomorrow, and that's on creating videos for scientists, community managers, and beyond. That will be tomorrow at 2 p.m. Eastern. So if you are interested and available to attend, please register for that. And thank you, everyone. It's been really great.
Yeah, thank you very much.
Thanks.